In this example, we want to find the exact value of sine evaluated at cosine inverse evaluated at 3 divided by 5. Again, first, we need to go ahead and look at cosine inverse. So cosine inverse evaluated at 3 divided by 5 is equal to some angle theta. This occurs if and only if 3 divided by 5 is equal to cosine evaluated at theta. Cosine evaluated at theta is equal to 3 divided by 5 can be represented using right triangles. So again, the adjacent side is going to have length 3, the hypotenuse has length 5, and by the Pythagorean theorem, the remaining side is going to have length 4. And the acute angle of this triangle is given by theta. Now that we have this set up, we can rewrite sine of cosine inverse evaluated at 3 divided by 5, replace the cosine inverse of 3 divided by 5 with our theta, and we'll get that this is equal to sine of theta. And since we have our right triangle corresponding to our angle theta, we can evaluate sine evaluated at this theta, which is going to be equal to the length of the opposite side divided by the length of the hypotenuse. So we'll get that this is equal to 4 divided by 5. And this is our answer. In this problem, we want to find the exact value of secant evaluated at sine inverse of 12 divided by 13. There's two different ways to solve this problem. First, we'll look at solving this problem by definition of sine inverse. First, looking at sine inverse of 12 divided by 13, this is going to be equal to some angle theta. This occurs if and only if 12 divided by 13 is equal to sine evaluated at theta. Again, theta is going to form the acute angle of a right triangle whose opposite side has length 12 and whose hypotenuse has length 13. Again, we can find the length of the adjacent side of this triangle by using the Pythagorean theorem. So we'll get 13 squared is equal to 12 squared plus, let's call this last side a squared. This is going to be simplified to be the square root of 169 minus 144, which is equal to a. And so we see a in this case is equal to 5. So now that we have our right triangle on all sides, we can go ahead and evaluate secant of sine inverse of 12 divided by 13. This is going to be the same thing as evaluating secant at theta. Secant is the same thing as the hypotenuse divided by the adjacent side, and we'll see that this is 13 divided by 5. Now let's look at an alternative way to solve this problem. Another thing that we can notice is that secant x is equal to 1 over cosine of x. Now we know that cosine of x is equal to the square root of 1 minus sine squared x, theta. And when cosine of x is positive, the square root of 1 minus sine squared x will be positive in the first quadrant. So we can rewrite this then as 1 divided by the square root of 1 minus sine squared theta. Now let's go ahead and take this statement and evaluate secant x at sine inverse of x. Now we'll get secant evaluated at sine inverse of x. This is equal to 1 over the square root of 1 minus sine squared evaluated at sine inverse of x. Because sine and sine inverse are inverse functions, these functions are going to cancel out, and we'll be left with this being 1 divided by the square root of 1 minus x squared. So if we evaluate secant of sine inverse of x at 12 divided by 13, we'll get our solution. So let me go ahead and start a new page and bring in and rewrite our secant of sine inverse x. Okay, so evaluating this, we'll get that this is equal to 1 divided by the square root of 1 minus 12 divided by 13, all of this squared. This is going to then be equal to 1 divided by the square root of 169 divided by 169 minus 144 divided by 169. And this simplifies to be 1 over the square root of 25 divided by 169, which is equal to 1 divided by 5 divided by 13, which is equivalent to being 13 divided by 5. And we see this solution matches with the previous solution.